Today I'll talk about the work that we have developed in the last months, which was concluded in Brazil. But part of the work was also done here, and you participated, so you may realize that something is really familiar. So that means that I will start talking about the self-managing architecture, which is composed by three main things, or three main components. The first component is a WSNs network application and resource management, which was developed there by their group. The dashboard that we are more or less familiar with, and the data analytics server, which is a server that I developed meanwhile. The second part, then over this architecture, I will discuss about its applications, or some applications that may explore the architecture. And the main one, which Madalena participated, was the reinforcement learning for controlling sensor nodes. We did the simulations, and finally in Brazil, I put it in practice. So based on the theoretical stuff that we prepared here, I did some experiments. So the first part, the self-managing architecture. Let's suppose, or let's imagine, what's a self-managing architecture. Let's say it has a sensor network, and the nodes deploy, or they send, they collect the data to the gateway. This gateway can communicate with the server, and the server has a connection with another server that can perform some data analysis. So just going step by step, the gateway receives the data from the nodes, transmits to the server. The server stores in a database, which can be accessed further, and it stays somehow protected. Then this server notifies, or it sends, or it forwards this data to another server, which is going to process the data. It's going to analyze the data, it's going to make something, perform some analysis, and will return a reaction. So, and then in the end, the server will notify the gateway about what to do. So this is what we need to have a self-managing architecture. We collect the data, we process the data, and we generate a reaction. The first problem is how to fine-tuning the wireless sensor networks. Each network is different. You know much better than me that it's hard to configure nodes and so on. So let's imagine one wireless, just to give you an overview of the problem. Let's imagine that we have this wireless sensor network, and these nodes are reporting data every 5 minutes. They are reporting data to the gateway. So I won't stress too much about the flows, but it's important to note that some nodes have more work than the others, and this has to be handled somehow. If I'm not handling, someone has to handle. Okay? And let's suppose in this case that these three nodes are working in their maximum workload. They cannot transmit more packets. For some reason, maybe the data rate doesn't allow them to transmit more packets. So, if we remember about the self-managing architecture, this, after some point, eventually, this gateway will transmit some commands to these nodes. And this command maybe it updates these nodes. And let's suppose that these nodes have to to transmit more often. So it's a bit bigger. So, but then, if you remember, these nodes were operating their full, their maximum workload. So, for example, we have to rearrange this data flow. So this is one problem that we have in self-managing architectures. This is one kind of problem. There are other problems, for example, if they may report to 2 gateways or 3 gateways at the same time. There are several things. And this is what they solved in Brazil. Your group did the first thing is the TinySDN. They have an SDN-based solution, and using SDN, they can manage control flow and data flow. So they put it separate, and they can think, for example, this component that stays in the middle of the operating system, it considers disruption and delay communication. It considers that the nodes may have low energy supplies, that they cannot, it's hard to fragmentate the packets, and that there may exist several controllers in the sensor network. And actually, this is kind of a feature as well, because you can add some controllers to improve the work, the operation of the system. And it also controls the data rate. For example, it considers if this node transmits more, it will start to have collisions and so on, so it takes the inland control in consideration. It has an inland control. On the top of this, they developed the wireless network application and resource management, which has a nice name, WARM. And so basically, this was their proposal, the original proposal, and this is how I migrated to our architecture. So the gateway has, there are 3 nodes. In fact, in the real implementation, there are 3 nodes here. Each one is running a different software, and the sensor nodes are also working with this platform. So the WARM itself, the framework, is represented by this middleware. So the manager communicates to the middleware relies on the SDN, and the SDN is inside the operating system. And the gateway can control everything. So it can schedule tasks, it can cancel tasks, it can request the state of the task. For example, if I schedule temperature or something like this, it has all the knowledge about what's happening in the network. And I can also request nodes characteristics. For example, I can also ask which nodes are in this region, which nodes can sample temperature, which nodes can do some processing, data processing. Okay. So there are 4 task types. The first one is a periodic. For example, I can ask the gateway to measure the temperature in sensor number 2 and send to sensor number 10. So the sensor number 10 would be the sync node in this case. Okay. It's a periodic. I just schedule and runs once and it's over. It can be periodic. I can say, please measure temperature in sensor 2 every 2 minutes and transmit to the sensor number 10. Then every 2 minutes, it will be scheduled in the nodes. It can be triggered, for example, measure the temperature, and if it's over 30 degrees, you report to number 10. Otherwise, you just don't do anything. And the last one is on demand. Okay, number 10 received all these temperature values. Please print. Or if you receive it like some measurements in the last minute, average them and print. So this is on demand. If it has received something, it will perform a task. So these are the 4 types of tasks that WARM supports. It's also interesting that they provide an API, so anybody can develop their own application. In this case, they provide, for example, in this case we are talking about temperature, but we can develop an application to report relative humidity, we can develop an application to calculate the average in the last 10 measurements before transmitting. We can do whatever we want under their constraints. So basically, there are some duties in the controller. It may not schedule more tasks than a node should support. It has to find, or it has the knowledge about which sensors are in a certain region, so it can inform the user about those nodes. And it also connects with a REST server. In the original project, they provide a REST server, so any user can access via API and program the nodes through the controller. Yes. So, what we get from this? We have the self-managed architecture. We have these 9 things. If we have this easy to change the nodes, to change their operation, we can easily add another sensor network. And at the same time, we may have remote users. The users don't have to be there if they can reprogram the nodes via API. Okay? So this is a more complete picture of what we have. So I explained now what they have done in Brazil. Now I start with the dashboard, the new version, and I can, in fact, because it works, there are some nice features that I want to stress a bit. The first one is the user access. So I will put the, you know much better than me, but I will put the user password. So we have the user access, and here we have all the statistics. For example, how many sensors are active, how many measurements we have in last hours, the alarms. We have the last measurements. There is one node which is reporting data in my room, and we have also the recommendations. So the process that is done in the other server is input here as a recommendation. So we have all this information here. We can also, we can also see the values and the recommendations. Okay, so this is just a new interface we can return. Just to stress a bit, the user access, the statistics, and the recommendations. So I won't spend more time about the dashboard, but finally we decided for a standard how to communicate with the dashboard. So basically, this is the standard. All the incoming data should be reported via API, and the dashboard now has the ability or the capacity to notify events. So anybody, if Tony creates a server and it turns the server to listen for a certain port, once the dashboard receives a measurement, it can notify Tony about the new measurement. So this is the standard. To input data, we use APIs. To output data, we use events and notifications. About the data analytics server, it was developed in R, as you could bet. And there are two recommendation types. The first one is the sampling interval, so it can recommend a node to sample more often or less often. Let's say if it's sampling every 30 seconds, we can increase to 6 seconds or 5 minutes and so on. And the other recommendation type is the acceptance threshold. It's something like if you measure that the temperature is 30 degrees, you don't have to tell me anything, because I know. Okay. So we have these two types. In implementation, we work with the first one, with the sampling interval, but there is the possibility to use this acceptance threshold. It receives TCP connections from the dashboard, so there is a server with an open TCP, an open port listening to TCP connections, and it submits its results to APIs, which are those provided by the dashboard. So there are some applications, if we think about the whole architecture. Mood scope integration, the first application. The mood scope integration is that, okay, it can somehow self-manage, but it can also provide recommendations for the users. Instead of recommendations that go to the gateway, the recommendations can be to the users. For example, in the automatic, there could be a recommendation for the owner or the owners that they should put more poison, or they should change one node, or something like this. So this is something apart from the self-managing stuff. The second thing is it's a new business that we can provide. It's sensing as a service. What I mean with sensing as a service? Since we can identify this user is remote, we can give him access to, for example, these nodes and to these nodes, and he will receive, or he will be able to see the temperature in this place, and we may charge him. So we are selling the sensing service. Okay. The other application is prediction-based data reduction, which is not worthless.
Useless.
Okay, useless is even stronger. I will show you. Basically, we have some applications, but before talking about the predictions, I close this self-managing transaction. Okay. So the second part, the part of the applications, especially predictions about what's going to happen in the sensor network. So we have this problem. Here we have one sensor measuring temperature in an office, and it looks like this. It's
Funny that is the opposite as here. Usually
here.
the night you have a higher temperature than during the day.
okay.
Well, no, maybe in Brazil during the day you have even higher temperature.
But then I will turn the air conditioning. That's why they call warm. So this was the problem. The temperature wasn't changing at those times, and it changed much more in the other times. So what we proposed with Madalena is the reinforcement learning. So how reinforcement learning works? We first observe the environment. We take an action. We observe the environment again, and we calculate how good was that action. And we repeat. What we take an action again, we run up to the first one. But then we take a new action, observe the environment, and calculate the reward, and repeat and repeat. So, for example, in our case, we make a measurement. We observe the environment, so the nodes make a measurement, makes a measurement. We take an action, which is, for example, adjust the sensing interval. If it's measuring every 6 seconds, it can measure every 2 minutes. We observe the environment again, make a new measurement, and we calculate the reward. So the reward here is based on this question. Is the difference between the last 2 measurements greater than a certain threshold? This is how we calculate the measurement. We have to scale the measurement, the reward somehow. So we can put some numbers. If it's if yes, we can say it's 1. If it's no, we can say it's negative. But we need a scale for this. Okay. But then we have a problem because this is not very smart actually. In this case, we are just taking actions, observing what's the reward, and it's not very smart. We can do something better because if we return here, we are not actually, well, if we do as it was, we are looking at the measurements here. But we can do better because we are actually interested at these times. Right? Well, we know that at these times, the temperature rises less. And at these times, it rises more. So we can improve, we can make something smarter. So, what else we can improve? By the way, just before, if we just consider the temperature, any sensor can do this. We don't need servers, we don't need R server, we don't need any robust programming or any robust data analysis. Any sensor node could just check the temperature, calculate the reward, check again, and so on. But we can improve. So we can consider some factors like the quality. We compare with the last temperature measurement. We can consider the hour of the day, which is kind of information that's not always available to the nodes. We can also consider if it's a working hour, and it's also not, usually you don't program your nodes with the working hours. And this is interesting because, well, in fact, in Brazil it starts at 9. I started even before, but I just turned on the air conditioning at 9 and goes until later. The day of the week, we can consider if it's weekend or weekday. We can consider in which sampling, which is the sampling interval that node is using, and we can consider its ID. So, but now there's too much information. We can filter. And to filter, we can use the random forest, because random forest can give us the variable importance. That is, we can filter to use only the factors that really matters in our case. How we do this? We first ask if we, well, the question is, if we aim at predicting the next measurement, if the next one will differ by more than 1 degree, which should we observe? This is the question. So for example, in scenario 1, we know that today is Tuesday, and the sensor node is measuring every 120 seconds. So will the next measurement differ by more than 1 degree than the current value? This is not easy to answer. The other scenario could be, for example, we know that today is not weekend and it's a working hour. Can we predict if the next measurement will differ by more than 1 degree? There is the best scenario, which is actually, today is not weekend, it's working hour, the sensor node is the number 3, it's measuring temperature every 120 seconds. So now we have some confidence to say if it's going to differ by more than 1 degree or not. So using random forest, we filter all these factors, and we finally use it on quality. We check if it's a working hour, and we check what's the sampling interval in this interval. So just going back to the loop, once we have which kind of observation we do, we can put it in a loop, and we use the co-learning to learn with the environment, with our actions. When we change the sampling interval, how are our rewards? And to do this, we use co-learning. And co-learning has mainly two parameters. The first one is the discount factor. The discount factor here it's used in co-learning. We make an estimation about how it's going to be our reward. Please tell me if I'm wrong. And the discount factor can tell, okay, you should consider more the past information, or no, you have to consider more the fresh information. So this is one parameter. We use it between 0 and 1. The other parameter is the learning rate. If we have a large or a big learning rate, we learn faster. It's like a baby that doesn't know anything, learns very fast. And when we ourselves get older, we decrease our learning rate. We can learn that fast. So we observed the learning rate and the discount factor, and in the simulations we checked how many percent of transmissions we could save using this approach. So this one was the result. I want to stress or to highlight these 2 points. When the learning rate is quite high, and if you cannot see the discount factor 0.1, we have these very good results, and they are much better than the others, than the average. Okay, so it's in this case it's quite important this pair of learning rate and discount factors. The other results that we got was the percentage of difference over the threshold. So if we don't want to make a measurement that will differ by more than 1 degree, the threshold is 1 degree. So we want to make measurements faster, to such that 2 consecutive measurements will differ by less than 1 degree. Okay? So this is basically here is the percentage of times that we failed. The percentage of times that we failed. Okay? So again, we observed the learning rate and the discount factor, and on average they have a similar behavior, but there is this combination, again, a high learning rate and a very small discount factor. Just for baseline, we can add how it performed when it was sampling every 30 seconds, every 60 seconds, 120 seconds, and 240 seconds. So this is very close to the best scenario that we could have in terms of percentage of differences over this threshold. So very good results. These in the simulations, and then we were very happy that the simulations were good, and we went to the real experiments. Oops. So we deployed these 4 nodes in the office. This is the air conditioning. It's very important because I was expecting that this node would vary a lot because it was close to the air conditioning. But in fact, this node varied a lot. Because, yes, exactly. And this one varied at the least. So, yeah. And I put this one close to the door because I expected some people to go talking about, and this was my computer, very far from the window.
And you don't put any sensor at the window?
No, actually the window is internal window.
Okay.
So it's not like here we have a forest.
But you got the worst place,
Yes, the remaining. Okay, it's how they deal with new people.
You are the last one, right? So you get them.
And it was full, so there were many people to put some noise in the measurements. So this is how the real experiment went. Basically here we have the 4 nodes, and here we can, it's still adjusting the best, it's still finding the best sampling intervals, but we can see, for example, here they are sampling very often, then okay, no, it's not changing too much, so let's try to sample less often, and more or less the same here, and so on. So this is how it works, in fact. So the results, considering their importance. Here we say that in the best case, almost 85% of the transmissions. In the worst case, in the number 7, that one that I liked a lot, we saved only 44%. But without saving that much, we got the best intervals. It's like a very conservative approach. So when it notes that the thing can go really bad, it samples very often and reduces these average difference. This is the difference between two measurements. Here is how many times we sample, or the difference was over the threshold. So in the worst case, 11%. And finally, the average difference between two consecutive measurements was 0.29 in the worst case, which is under our threshold. Our threshold was 0.5%. So basically, if I was the owner, I would be happy if the program would be to sample in this way. Meanwhile, we also checked the time, because of course the information leaves the gateway and takes a while to process the data and create the recommendation and inform the nodes back. So here in this case we just check the average clock drift in the sensor nodes. It's more or less 1 second less than they should. So instead of sampling every 30 seconds, they sample every 29 seconds. And this is the introduced delay. So this is the time that it takes to complete the whole path, to leave the gateway, to process the data, and make a new recommendation. In the worst case, because in this case it was even better. So, in conclusion, it's possible to create a smart sensor network that can self-optimize, optimize, and avoid unnecessary transmissions. Second, while the sensor network specific knowledge is dispensable, we don't need anybody to program these. We just plug the nodes and they work. There is a new business opportunity, which is the sensing as a service. We can sell this information to any user that has access to the dashboard. And it can be extended to applications that require more computing power in sensor nodes, because the worm has this API, and anybody can develop a new task type, a new task that will run in these nodes, which can be a prediction, which is not useless. And the dual prediction would be the anchor in this case. So we can extend these to new scenarios. publications, the self-managed architecture for essential nodes based on real-time data analysis. This was a demo proposal that we did with Tony, and it was accepted. So I'm going to present if the demo works.
We hope.
I need your note.
No problem.
And there is another publication that we did with Madalena, which is about the simulations using reinforcement learning to control sensor nodes. And the publication that we did with their partnership, which is called Empowered Self-Managing Wireless Sensor Networks, which is basically everything that I presented now. Okay.